Am I audible now? Hello? Hello?
Yes, sir.
Okay, so the voice is clear right now?
Yes, yes.
Okay, yeah. So what I was telling is, so LH will be in the left hand side and LH will be again on the right hand side, and we will have, all right. So these two cancels out and one will be equal to 1 plus epsilon 1, and if you take this part here, it will be 1 by 1 plus epsilon 3. Is this clear now?
Yes, sir. Got it.
Okay, yeah.
So there is one another doubt,
Yeah.
sir. In this same slide, I mean, कैसे बोले यार? सर वो जो स्लाइड है उसके नीचे वाले स्लाइड में एक है टॉपिक जिसमें नॉन कोएक्सियल डिफॉर्मेशन है उसके थोड़ा सा ही पहले। हाँ हाँ इसके
This one?
नो सर इसके हाँ ये सर यही वाला।
Huh.
इसमें सर ये डाउट है मुझे कि इसमें सर लिखा हुआ है कि देयर आर टू लाइंस नेवर डिफॉर्म्स बट रोटेट। सर
Yeah.
तो ये समझा रहा कि कैसे ये
Okay.
डिफॉर्म होने पर रोटेट हो
Okay.
जाए।
Okay. Can you mute yourself? Because there is some kind of motor. Yeah. Yeah. So what happens here is that, say, this part of the ellipse will, this part of the circle will be compressed, right? And this part of the circle will be extended, right? If you are having a pure shear condition, this part will be compressed and this part will be extended. So there will be one part in that unit circle which will neither be compressed nor be extended, so that that particular part will not be deformed. Say for example, you have a circle here, right? And you are deforming it, right? So eventually you will get a shape of something like that, right? So this part will be extended and this part will be compressed, right? So in that circle, like if this part gets compressed and this part gets extended, there will be one point in between somewhere here. There will be one point which gets neither compressed nor decompressed, nor extended. Are you getting this?
यस सर।
हाँ, एक जगह रहेगा जो मतलब बढ़ेगा भी नहीं लेंथ में और घटेगा भी नहीं. So that particular line, that particular portion is called lines of no finite deformation or something like that. No finite longitude, lines of no finite longitudinal strain. So this, as this circle gets more and more deformed, so these lines will rotate and it will try to align more or less. If this gets extremely flattened, so it will be more or less parallel to this axis, right? Is this clear now?
यस सर क्लियर।
Okay,
थैंक यू सर।
so can I proceed with the stress part?
यस सर।
Okay, yeah. So where was yeah, Hooke's law. Yeah, all right. So but the interesting thing about this stress is that, like, if you have a body and you apply force to it, so we are not going to consider the force that is applied on it, right? So we will be considering all the force that the body is exerting on that object or whatever mechanism that we are using to apply the forces on. So these force are called reactive force. So all the calculations that we are going to do will be on the basis of this reactive force. All right. So if a body is under stress, what will happen? It can have two kinds of force. So say for example, this reactive force. So this is basically from Newton's third law. This is basically two kinds of force that can act on a body. One is the body force and the other is the surface force. So body force is responsible for volume change or volume distortion or something like that, and surface force, this acts only the outer part of the body, it acts on the surface. So these two force goes hand in hand and they bring about this deformation, right? So if we have an irregular body like this, and so how will you go through it? How will we go to calculate the stress of that particular of this whole body? So the usual approach is that um, we consider an infinitesimally small volume of object, and from that we just calculate the different components of stress. All right. So if some kind of force is exerted on this body as a reaction, so what will happen is that, so let's say these are the three coordinate axes. So what we will do is, so one component will be perpendicular to these planes, which are, say for example, if this is perpendicular to x1 and x3, so this force will be, or this stress will be termed as sigma 2 2. So this is eventually, this will be parallel to the x2 line, and if that is parallel to the x1 line, similarly we will have sigma 1 1 and we will have sigma 3 3. But this does not really so all these forces, if they act, it can decrease or increase the volume of this body. Are you getting this? So there might be other forces related to the condition which might be able to rotate this object. Are you getting this? This part is very crucial. So what I mean is, suppose this is one body and you only have forces acting perpendicular to these planes. So what will happen? Its body might get bigger in size, something like that, or it might get shrinked, something like that. But there will be no rotation. If some kind of force is required to rotate the body, that should act along the plane, not perpendicular to the plane. All right? Are you getting this?
Yes, sir.
Okay. Yeah. So again, what we do is we differentiate, or uh, the component divisions we do along the planes as well. So, and we will always do this we will always do these components parallel to the axis, always, right? All right. So this we will call tau 2 in this direction, and sorry, T2, this will be called tau 3 1, and this will be called tau 2 3. This will be called tau 2 1. This is called tau 1 3. This is called tau 1 2. So are we familiar with this nomenclature? Why this is 1 2, why this is 2 1, something like that? Are we familiar with this
Yes,
nomenclature?
sir.
Yeah. So this is
Yes,
how,
sir.
yeah, this is how we divide the stress component, and this is how we calculate, like for this is how our calculations becomes much more easier. But one thing is very important when we deal with this strain kind of stress kind of problems, stress related problems, that is linear transformation. So in
Hello,
linear, yeah,
sir. I have a question that
yeah.
what is the source of these shear forces? I mean, मतलब परपेंडिकुलर फोर्स से हम लोग का shear force कैसे जनरेट हो जा रहा है?
So actually what happens is that, suppose you have a body and you apply a force, right? So you are applying this force, right? So it's impossible for even if you have a very regular body, it's impossible that everything that you are applying the force exactly perpendicular to this plane, right? So there might be some kind of angle, however small it is, there will be some kind of angle, right? So that produces the shear component. So in nature, you won't get pure shear or simple shear condition. We always get a little bit of mixture of both. All right. So in nature, we don't get like this beautiful rectangle type of objects, right? So there are two components, and we study it separately. We calculate those separately, and then we add them up so that we get the final result. This is how we do these calculations. Otherwise, if you don't have a shear force, so the porphyroclasts like garnet, they won't rotate, right? And rotation we see is a very common thing in geological samples, right? Is all right?
Yes, sir. Yes, sir.
Okay. Yeah. So about linear transformation, what we do is, suppose you have a stress matrix of so this is how we write a stress matrix. So these will be called as the principal stresses, and this will be called as the shear stresses. All right. So suppose, how will you represent a stress matrix? So the easier way to represent a stress matrix is that by the use of basis vectors. So do we have idea about vector space? Are you on the same page regarding vector? Like what is a vector and how we can use it in the calculation of stress? Hello? Am I not audible?
Yes, sir. Yes, sir. We know vector.
Yeah. So we know like what is basis vector, right? So basis vector is basically the unit vector.
Sir, I cap, J cap, K cap.
Yeah, those are exactly, those are the basis vectors, right? So basis vector is the vector that you need to represent a space. Suppose you have a 2D space, so you need two basis vector, that is, one is I hat and the other is J hat, right? If you have these two vectors, then you can form this 2D space. For 3D space, you need I hat, J hat and K hat. All right. So these are basis vectors. So what happens is that if you have a, say for example, if you have a matrix like this, all right, and you have a D matrix, which will be like suppose it has 3 0 1 2 value, right? So if we want to, you know, go from initial configuration to the final configuration, after the D or the deformation, how to represent that? That is our goal. So in the initial configuration, we have this space, this undeformed space, right, where you have some x, some y, some values like these. You have these squares are very regular. Assume these squares are regular, all right. So, and now after the deformation, you will get a if you deform this by some way, if you deform this, you will get a space which will be different from this one. So these beautiful squares will be deformed and you will have a new positions. All right. So if we do this transformation, like if we know like this deformation matrix operated on this media, what will happen? That we will get new coordinates x dash and y dash. And how to get that? So x dash will be the simple matrix multiplication, will be 3x plus y, and y dash will be 0 times x plus 2y. So any coordinate on this point, if we want to know what happened to that coordinate after deformation, we will get the information from these two equations. All right. So if you look very closely,
That will be, sir, that will be 1 into x.
that will be 1 into
Oh, sorry.
y.
So y dash, y coordinate. So am I right or?
So 3 times x, 1 times y, again 0
Okay,
times
okay,
x and 2 times y.
okay,
Okay, simple matrix multiplication. If you want to, you know, like what is happening here, it's happening like this. X dash is basically is equal to 30 of x, and y dash is equal to 12 y, right? So the x components will be 3x and 0x, and the y components will be y and 2y. So if you just add them up, right, so you will get this equation. All right.
okay.
Okay, yeah. So if you look closely, like 3, let me write it again. So this is the deformation matrix. So forget everything else. This is the deformation matrix. So what happens is that this small line, which with this small unit x, or say for example, consider it as I hat, it's produced a new I dash hat, right? So what happens? It got extended in this direction, like this, and the j cap or the j hat which we had previously, we have a new j hat, right? So it got increased 1 unit in x direction and 2 unit in this direction. So it is the new position, right? And all the axes and this space will be something like that, right? So this space will be converted to this space. So if you put a body somewhere here, it will be deformed and it will become something big like this here. Are you getting the idea now? Hello?
Sir, will you please repeat?
Yeah, all right. Suppose you have an undeformed matrix, undeformed array, right? There is no deformation. This is the initial array, right? And after some kind of deformation operation, your array changes to something, right? We don't know what will be the configuration of this cage, right? Are we clear up to this point?
Yes, sir.
So suppose your deformation matrix is somewhat like this. So we intentionally use this matrix. Otherwise, we can use anything, like in 3, we can use 4 or something like that. But this kind of linear transformation is called shear transformation, because in the x, you will, sorry, the x basis will only get extended, right? So if you have, so imagine you are stretching this part on the x direction, right? So this unit square will be 3 times longer, right? If this is the initial length of that square, it will be now of this length. It will be 3 times longer, right? And the y and this part will be 1 times in the x direction and 2 times in the y direction. So it will be something like that, right? If you had, if we have here, if we had 0 here, then it will be only this much, right? There will be no this component, right? It won't be like that. Suppose we have a matrix like this. What will happen now? Can you tell? Hello?
Y will be stretched to 3 times.
So y will be extended into 3 times in this direction, and x will be what? X will be somewhere here. All right. So this is how. All right. So this will be the new basis vector. Instead of this, we will have a new basis vector like this. So if we repeat this basis vector, we will get this entire space. Now if we repeat these basis vectors, we will have an entire different space like this one. So everything will be, so what happens if we do linear transformation? Straight lines, they remain straight. There is no shift of origin. So these are the two rules of linear transformation. All right. Are we clear now? So if we have a body somewhere here, so suppose this is a body. So after this operation, this body will be stretched and it will be something like that. It will be something like that. So this entire body becomes something like that after the operation of this stress matrix. Are you getting it?
Yes, sir.
Okay. Yeah. So if we do the linear transformation, we know we can represent each and every point after the deformation, right? So if we want to calculate, but there is a catch, like there will be one or more than one particular direction which won't be changed. Like here, this y direction is changed into something like that, right? But the x direction did not change, right? X direction remains the x direction even in the deformed matrix, right? This is the x direction, but this is the previous y direction which is changed. This was the previous one and this is the new one, right? So there will be directions which won't be changed. It will be either stretched or it can remain same depending on the D matrix. This direction, there will be some direction which won't be changed. Those directions are called eigenvectors, right? And the ratio of the vector, like how much the new eigen, how much the what is the new position of the say for example any point, what is the amount by which it got stretched, that will be called the eigenvalues. Okay.
Hello.
Yeah.
Sir, please repeat this concept.
Okay. So the thing is, if you deform one matrix, okay, I will use this. I will use sir's lecture. I think that will be easier. Okay. So, okay. Can you see here? Hello. Can you see?
Yes,
Yes,
sir.
yes.
Yeah. So now follow this purple line. So these gray lines. Can you see the gray lines, or should I zoom it? Should I zoom it? Yeah. So if you follow this purple line, it did not change its direction. So this point is now, this point is now here. So it only got stretched. So it did not change the direction, right? Say for example, here it got stretched by 3 units. It did not change the direction. So yellow lines represent the new configuration, and the gray lines represent the old configuration, right? So in that new configuration, we are seeing there are definitely at least two directions which did not change. So whatever element that falls on the direction, it got stretched by 3 units, and here it got stretched by 2 times root 2 unit, right? So these directions are called eigenvectors, and the amount by which it got stretched is called eigenvalues. Is it clear now? Hello?
Yes, sir, please repeat it.
Okay. I'm going real slow now. What is this gray, what should I say, gray cage or gray kind of this lines? What are this is the initial configuration of the body, right? Suppose you have a body like this, and you made some kind of mark on it, some kind of gradation on it. So imagine these gray lines are those, right? Are you clear?
Yes, sir.
Yeah. So now we have some kind of deformation event. Okay. Suppose I deform this body in some way, right? So these yellow lines will be the new configuration. So this line, it will be rotated and will fall on this line, but this line will be stretched and it will become these yellow lines. Are we clear?
Yes, sir.
Okay. So if you follow, like, say for example, if you follow this line, this particular blue line, all right, can you see this blue line?
Yes, sir.
Yeah. So now it got stretched and it is here, because this point is, sorry, I'm wrong. So this point is somewhere here. So this is the first now it's a quadrilateral rhombus or a parallelogram. So this is the first, this is the point, right? So this point is now here. Are we getting this?
Yes, sir.
So if you see, so this direction is not this the same direction. So it got rotated, right? It got rotated by some angle here. All right.
Yes, sir.
So if you plot all the possible vectors on this space, you will find that most of them got rotated. They changed their initial course. But there will be some directions in which they did not change the course. They are on the same course as they were previously. Say for example, this line. This line, this red line, can you see the smallest square here? The square here. Can you see this red line?
Yes,
Beneath
sir.
this, yeah. So it got stretched and it is now here. It did not change its direction. Did not change its direction. It just increased in length. Where it was 10 point has become 30. So it is 3 times of the previous configuration, previous dimension, right?
Yes,
if
sir.
you if you follow this purple line, it also increased its length, but it did not change this direction. But this green line changed its direction. It's here. This yellow line changed its direction. It's here, right? It did not change.
Yes.
So the direction in which we do not get any change are called eigenvectors.
Okay, sir.
Okay,
Yes,
and
sir.
the value of those, like the amount of which it got stretched or diminished, it can get diminished if depending on the deformation matrix. It's not required, like, sorry, it will always get increased. It might get diminished also. So that particular amount is called eigenvalues, right? And we are going to see how to calculate the eigenvalue and the eigenvectors.
Okay, sir.
Okay. Yeah. So to calculate the eigenvector and eigenvalues of this matrix, what we will do is we will assume that lambda is the eigenvalue. All right. So 3 minus lambda, it will be 0, right? So if this is 0, then the determinant of this will be 0. So that means 3 minus lambda into 2 minus lambda is equal to 0. We know how to calculate the determinant, right?
Yes, sir.
Yeah. So what will be the value of lambda? It will be 3 or 2, right? If we solve this equation, it will be either 3 or 2, right? So now we have the eigenvalue. It's a quadratic equation. It will have two roots. So it is not necessary that you will always have two roots. You might get one root, only one root, or you might get no root, right? Say for example, for a rotation along the z axis. Say for example, if this is x and y, so along the z axis, if you rotate this 90-degree, if you can check it, if you can do it in your copies later, if you rotate it 90-degree, you won't get any eigenvalue. That will be imaginary, right? If you do not get, if you try this yourself, if you cannot do this, if you fail to do this, just inform me. In the next week I will show you why we won't get the eigenvalues in that direction, right? So now we have the eigenvalues, so we'll rewrite the equation.
Sir,
Yeah.
so if we get eigenvalue equal to, imaginary eigenvalues,
Hmm.
so what we can say about that?
We can say that there is no direction that remained. See, yeah, that's a very good question. Say for example, what is the concept of eigenvalue, eigenvectors? That there will be some direction which remained constant, right? So no eigenvalue implies no eigenvectors. Zero eigenvalue, I mean, if this equation does not have a real root, then there will be no real eigenvector. So there will be no possible direction where we can get like this axis or this direction remained same, right? What we did here, we just rotated it. So we rotated this axis, right? So the new configuration, is something like, so this axis went here and this axis went here, right? This is the condition, we rotated this, right? So if you rotate the axis, what will happen? There will be no direction which will remain constant, right? So if you get only rotation, then there will be no eigenvector. All right.
So we can say that eigenvector direction of eigenvector are those along which no rotation occurs.
Yes. And that's why we calculate the eigenvectors. That's why we calculate the eigenvalues. Because suppose you have a body like this and you deformed it some way, some kind of deformation happened, and the body is now like this. So what will be the axis of rotation? The eigenvectors will be the axis of rotation.
Yes, sir.
Okay? Because on that axis nothing changed. The direction did not change. It may get stretched, but it did not change. So those will be the axis of rotation. Here we are not getting the eigenvector because we are assuming a space that only contains x and y. There is no z. If we have an equation of a 3 cross 3 matrix, and the equation will be, then this equation of lambda will be a polynomial of order of power 3, right? In that case we will have that eigenvector that will be the z axis, that will be 0 0 1. This will be the eigenvector because we rotated this along this z direction. We're only considering x and y, that's why we are not getting any solution for the eigenvectors. Are we clear?
Yes, sir. And that value can be 002 or 003.
Yeah, that value is exactly, that value can be, because but if we like eigenvector is the basis of the all possible eigenvectors, right? 002 is also eigenvector, 003 is also eigenvector, 00 minus 4 is also eigenvector. But if you say eigenvector, we usually just use the basis of that particular eigenvector. So that's why I have written 001. It can be 0.5 also, right? But it's better to use 001, because otherwise your life will be easier. Like in the next calculations, when you use those eigenvectors, the calculations will be easier if you use unity. It's not always possible to use unity because, see, you may have 0.5 here, you may have 1 here. Suppose this is the eigenvector, what will you do then? For the sake of calculation, you will just consider like this is the eigenvector, so you get one unity somewhere, right? All right.
Yes, I got it.
Yeah. So are we clear about the eigenvector and eigenvalues?
Yes, sir.
Okay. So no, I think I missed it. Like how to calculate the I showed you how to calculate the eigenvalues, but I did not show you how to calculate the eigenvectors, right?
Okay, sir.
Yeah, so this will be transformed to, if
Yes,
we
sir. And
consider,
also, sir, I don't understand why we subtracted lambda from 3 and 2.
why subtracted lambda from 3 and 2?
Yes, sir.
Because, yeah, because, so this is the new matrix, right? Lambda time x, that is equal to s, that is the previous matrix, right? Or deformation matrix, right? So lambda times x, what is the, like in the eigen, so the structure of lambda is somewhat like this. All right, so this can be represented as lambda times this. So the unit matrix times lambda. All right,
Yes, sir.
so if you take this part, so this is how we got this one, and if you take this part in this side, you will get s minus lambda times the unit matrix into whatever vector it was, and then that will be 0. So if that is 0, then so this, this matrix becomes of this form, right? If you have two different matrices and you minus them, what will happen? It's because the other parts of the lambda is 0, right? That's why only in this part you are getting this 3 minus lambda and 2 minus lambda.
Yes, sir. Clear.
Okay, so where was I? Yeah, so now the, if we consider lambda equal to 3, so the matrix becomes 0 minus 2 minus 2, is it? Yeah, 0 minus 2, no, not minus 2, 1, again 0 and minus 1. All right, so this is the new matrix. So what will it be? It can produce one x and y. So if we, so what will be the equation from these two? Can anyone tell? Can anyone tell?
Mm, y, I mean, matrix में y and minus y.
Yeah, so the x will be, like the first equation will be y equal to 0, and the second equation will be minus y equal to 0, right? So what is the line in a Cartesian plane? Say for example, if this is y and this is x, what is the line where, or what is the vector where y becomes 0? What is the vector? What is the line? So y is equal to 0 is
Every line
the
pass through origin.
passing through origin, and suppose if you have this line, will it be y equal to 0?
Not the whole line, but at origin.
No, the whole line has to satisfy this equation, right?
To z
Y,
axis. I think z axis will be.
no, not z axis. There is no z axis here. It's a 2D problem because we have only 4 elements here. Is the x axis?
Yes, sir. X axis.
Yes, it's the x axis. So x axis, that is 1 0, will be one eigenvector. All right, and what will be the other one? If we consider lambda equal to 2, so this matrix becomes 3 0 1 2 minus 2 minus 2, so it becomes 1 1 0 0, right? So what will be the equation here? X plus y equal to
0.
0. Yes. So in the y equal to mx plus c format, what will be the so x will be equal to minus y. So any line like this, so this will be 45-degree, where x is equal to minus y, or minus x, it will be equal to plus y. So this will be the other eigen vector. So we have this one and this one. So 1 minus 1 and 1 0. These are the two eigenvectors. All right. If you see the lecture, remember I was talking about this purple line and the red line. So these are the two eigenvectors. We did not change their direction.
Sir, do we have limitation on number of
No,
eigenvectors?
no. Depending on your deformation. Say for example, you have this matrix, all right, and what you did is you just uh, what you did is you increased it, right? You increased it like that. Okay, so what will happen? No direction will change. If you only increase that, no direction will change, right? There is no rotation involved.
Yes, sir.
So what will happen? Any possible direction will be the eigenvector, right?
Yes, sir. But
If you increase,
if we try to calculate eigenvector, then what result we will get?
sorry,
If we try to calculate using mathematics, then what kind of result we will get?
what kind of result you get? I'm not getting your answer, question.
Like if we have two eigenvectors, then if we solve, we will get two vectors, and if it is imaginary, we will get no eigenvectors. But in this case, we will get infinite. So how is it possible that we will get infinite eigenvectors?
Say for example, imagine a deformation matrix where everything will be stretched. Imagine one deformation matrix where everything will be stretched. So only you are having a volume strain, say for example. So what will be the deformation matrix? Right?
Yes, sir. Yes, sir.
So if we calculate the eigenvector here, right? Right? 3 minus lambda, 3 minus lambda. So this will be the determinant,
Yes, sir.
and lambda will be equal to 3. So if you put this value here, all becomes 0, right? So x will be equal to 0, y will be equal to 0, right?
Yes. Yes, sir.
So in this case, you have infinitely many solutions, right? This is one special case. This won't happen in their problems. Like we won't give this kind of problems because this is not a natural case. This is just a special case. But this will be the scenario in that case. Are we feeling it? Like what are we trying to draw here?
ये सर बस जस्ट यहाँ पे थोड़ा कंफ्यूजन हो गया, x इक्वल टू 0 y इक्वल टू 0 से हम ये कैसे कंक्लूड कर पा रहे हैं कि इनफाइनाइट सॉल्यूशन होगा। Infinite.
So these are the two equations, right? Like these are the two equations where I'm sorry, this is not, I'm sorry, this is not what you will get. Like
Yes sir, we will get
what
0 is equal to 0.
yeah, so it will be there will be no equation to write, right?
Yes sir, I got it.
Yes. Yeah, right. So all the possible directions will be the eigenvectors, but there will be eigenvalue, that is 3, right?
Yes sir.
Yeah. Yeah. So are we clear on the eigenvector and eigenvalues, so that I will move on to the last part of today's lecture?
Yes sir. Yes sir.
Okay. So have you heard about Kronecker delta? What is Kronecker delta? So Kronecker delta is, are you familiar with this kind of notation, del ij?
No sir.
These are called index notation, right? So you don't have to write the whole matrix. Suppose you have a matrix like 3 2 1 4 5 6 7 8 9. If you have a matrix like that, so if you want to call out any element from it, say for example this is matrix M, if you want to call out any element from it, then M11 will be equal to 3. So the first part will represent the row and the second part will represent the column, right? Now what will be M23?
6.
Yes. So this is how index notation works, okay? And this is how this sigma 11, sigma 12, sigma 13. So we all use this index notation here, right? So sigma 11, this whole matrix we can represent with just sigma ij. So Kronecker delta is a delta where if and only if delta is equal to j, I equal to j, then del ij becomes 1. Otherwise, for all the cases, if I is not equal to j, then del ij becomes 0. This is how Kronecker delta is defined. I am not sure about the spelling, but I guess this is the spelling of Kronecker delta. All right. So this whole thing we can represent like this one, okay? So we have done this for the 2D problem. So for 3D problem, things becomes things become little bit complicated. So this will be the equation if we want to get the determinant of this matrix, right? And that will be equal to 0. So as we have seen that there will be one polynomial of degree 2, right? So in this case, there will be one polynomial of degree 3, of order 3, right? So the highest degree will be 3, the highest power will be 3, all right? Just replace this sigma with lambda, right? Are we getting this? Hello?
Yes sir.
Yes,
Okay,
sir.
yes. Where was it? Yeah. Yeah, so and like every polynomial equation there will be some constants. These constants will be called invariant 1, invariant 2 and invariant 3, right? So let's not go into the detail of how these invariants are related, but let me tell you that invariant 1 is related to the lithostatic pressure. This is not equal to lithostatic pressure, but this is related to lithostatic pressure, right? Or mean stress, all right? And invariant 2 will be of form something like this. So if we if we calculate uh, this part, it will be somewhat like this, right? So this is called von Mises criteria. So this invariant 2 will tell how your rock is deforming. Is it deforming in a brittle manner, or is it deforming in a plastic manner? And the most complicated complicated one is the invariant 3. So we don't use it in structural geology like very easily. But if we need that, I don't know what will be the cases where we will be needing this I3. If you want to know, I can go learn and then tell you, but I don't think you need that. All right. So now are we familiar with the different invariants? Why is it called invariance? Any idea?
No, sir.
Because these values does not change. Right? I1, I2 and I3, after the transformation, after the linear transformation, these values, they do not change. That's why they are called invariant. All right. So I think we are at the last part of today's lecture. So there is a little bit correction. There will be one little bit correction on the slides, like whatever sir taught you. Uh, yes. Can you see this slide? Can you see this?
Yes, sir.
Yeah. So the shear stress, if you want to calculate the shear stress, this is not so this is not right. This line is not right, properly written. So what will happen here, if this is the theta? So have you gone through this lecture?
Yes, sir.
Yeah. So didn't you find this like this error?
I did not attended this lecture yet.
Sorry.
I have not gone through this lecture, so I don't find the error.
Okay. Yeah. So if you like deduce the components along sigma 3, so what will be the force will be sigma 3. Do you know like how this is happening, and have you read this somewhere else? Otherwise I'll just tell that this will be the shear stress, not this one, not this one. All right. So sigma 1 times sine theta cos theta minus sigma 3 times sine theta cos theta. Just that. Otherwise it's simply written here like how to get these equations, right? If that is okay, I'm not going to explain this. Otherwise I'll explain that.
Yes, sir. Please just tell us the correct one.
Yeah, this is the correct one. I'm telling this is the correct one. So the equation will be sigma 1 minus sigma 3 into sine theta cos theta, right? For the shear stress tau, this will be the correct answer. Like this is wrongly written here. This line, only this line is wrongly written here. Nothing else. Everything is all right. Just this line, there's a mistake.
Okay, sir. Got it.
Okay. Yeah. So anything else about today? Otherwise, I'm going to end the class because it's 15 minutes past 7. So if you have any doubt, please.
No doubt, sir.
No doubt. Okay. Anyone else? Anyone else?
No, sir. All clear.
Okay. Yes, so there is one feedback form that is floated time to time. If you are happy or unhappy with these tutorials, please give feedback there. And there is one discussion forum that we can use like 1 hour per week. I think is very little time, to discuss all the doubts and everything. So we can use that discussion forum efficiently. You can post your doubts there, and we can be prepared, like I can be prepared, or we can answer there. If that is not answered, then I can be prepared and answer it here also, right? So we will be, that will be more efficient, efficient, I mean the efficiency of using these hours will be more, like if you use that discussion forum also, right? So I encourage you all to use that discussion forum, and if you do not have anything else, then I'm going to end the session. All right.
Yes, sir.
Yeah, well, so I'm ending the session. Thank you very much. We'll see you in the next week. Okay, yeah, good night.